In this video, we are going to be talking about chairs. A chair is just a different way to draw a cyclohexane. In my experience, this is one of the most frustrating things to learn and get down in organic chemistry. So I'm going to show you how to draw a chair and then how to recognize and remember which positions are axial versus equatorial and how to draw the substituents on it. So to draw a chair, how I always start is by drawing one line slightly at a downwards angle. Then about halfway through, you're going to draw slightly down below another line, try to make it parallel and hopefully about the same length. It's totally okay if it's not perfect. So repeating that, you're going to draw a parallel line, you're going to draw one line, and then right below that, starting around the middle of it, you are going to draw another line and try to get it as parallel as possible and around the same length. Next, I have seen a lot of people draw chairs like this. You're tempted to just draw a triangle right here. You're tempted to go straight down and just connect here. That's not correct. I mean, it's fine if you've been doing that, but the best way to draw it, so again, your parallel lines, and instead of going straight up, you are going to go out a little bit. Okay? You're going to go out a little bit, not straight down, and then you're still going to connect them. Another way to remember this, you draw your parallel lines, and then you want to draw another set of parallel lines at an angle. Okay, so do you see how these lines are also completely parallel with each other? And they are attached to our other set of parallel lines. Finally, you just connect the two. I'm going to start from scratch. You draw a line slightly going down, and around halfway through it, you want to move down a little bit and start drawing another line around there. And try to get it hopefully parallel and around the same length, just eyeball it. Next, I know that a lot of people are tempted to go straight up and connect the dot, go straight down and connect the lines, okay? Don't do that. Instead of going straight up, maybe have the urge to do that, look at it and be like, that's not right. I want to go out, okay? Instead of going straight down, you go out. So you're going to go slightly out. You're going to go slightly out. Then you're going to connect the lines. That is how you draw a chair. Now, let's talk about how to draw substituents coming off of this. So for right now, we're just going to have all of our substituents be hydrogens because that's what it is right now. We can have it either being axial or equatorial. If it is axial, it is on an axis. It is either straight up or straight down. If it's equatorial, it's going to be at different angles, just literally anything except for straight up and down. You kind of have to memorize where to put the upwards one being axial, where to put the downwards one being axial or equatorial. However, I usually like to start with these because you must have the one going up straight through the middle. Why? You can't have something like a substituent being coming out to the sides or like this. That's not how it works. So if you have a substituent coming up, it must be axial. If you have a substituent on this one, if it's coming down, it must be axial on an axis. On every single carbon, you are going to have one carbon or one substituent coming up and another substituent coming down off of it. And on every single carbon, you are going to have one axial and one equatorial. So if we're starting here, I know that going down, it must be axial. So the one going up can't be axial also. That looks stupid and it's wrong. It has to be equatorial. How do you know what angle to draw your equatorial positions at? Sorry. It is going to be parallel with whatever's around it. Same here. If this is axial going up, the one going down must be parallel with these. So that's a good place to start. And another way to continue remembering it, you can't have, so do you see how this guy is coming up and then this guy is coming down? We'll start with this guy coming up. It's equatorial. My substituent coming up on here, because this one was equatorial, it must be axial. You can't have two substituents going up and both being axial or both being equatorial. It alternates. So because this guy coming upwards was axial, this guy coming upwards can't be axial. It must be equatorial. And again, on every single carbon, you're going to have one substituent coming up and one coming down. One must be axial, one must be equatorial. So I'm going to bring it back to this carbon right here, okay? So as we said, we have a substituent coming upwards and it's axial. So this means coming down, our substituent going down must be equatorial. We can't have something also axial. That looks stupid and it's wrong, okay? We have this guy coming up and then going down, it must be equatorial. And I'm going to draw it like this. And I'm sure you're wondering, why did you draw it at that angle? It's going to look somewhat parallel with that one. Okay. If you can just remember, start here, this guy going down, okay, he is axial. So here, this guy going down, equatorial. This guy going down, axial. Why? Because the one going down here was equatorial. So this one must be axial. So this one must be equatorial. So this one must be axial. So this one must have been equatorial. So this one was axial. You can do the exact same thing with going up. If you know that this right here, or we could start here, honestly, this is up and it's axial. So the one going up here must be equatorial. How do I know that angle? It'll kind of go in line with that. Again, it doesn't have to be perfect, but it's just a good way to remember what it's looking like. So again, up is axial. So here, up must be equatorial, axial, equatorial, axial, equatorial, and then axial again. And then you see this guy's going up. Well, then that means the equatorial one must be down. Something like that. Get in the habit of understanding these things and making these connections. Hopefully, you can just pick one that you really remember and then figure out the other positions based on that. All right, when we are converting some sort of cyclohexane with actual substituents to a chair, and there's stereochemistry involved, you need to know whether your line goes up or down. Dashes go down. If it is on a dash, it goes down. So depending on how you number it, if you have something on a dash, it must be going down. So let's say we number this as carbon 1, okay? This will be carbon 1, 2, 3, 4. If I label this as carbon 1 right here, this methyl must be this, okay? And then that becomes that CH3. And then on carbon 4, so we have 1, 2, 3, 4 right here. We have a wedge, a methyl on a wedge. If it's on a wedge, it's going up. So that means this must be our methyl. If I were to number this differently, okay, you could have numbered this 1, 2, 3, 4. You could have had this be carbon 1, 2. It doesn't matter. It's not that deep, okay? Just pick one. If I were to start numbering it here, having this be 1, 2, 3, 4, and then 5, 6. Let's have this guy be 1 for 1 second. Our substituent going down. So again, this guy, it is going down. So now this one is my methyl. And then on carbon 4, the one going up is also equatorial. Do you see that? This is equatorial. So now we have a CH3 equatorial and a CH3 equatorial. So I'm going to just draw these without all the hydrogens. So my parallel lines, starting about halfway down, trying to make them as parallel and same size as possible. Up, connect. So that's kind of what my chair will look like. And I'll do one again. That's what a quick chair will look like. Here versus If I were to ask you what is the most stable one, the most stable, your most stable has the most groups, and the biggest groups are equatorial. Why? Because they're hanging off to the sides. They're not bothering anyone, okay? Whereas if they're up and down, they're in the plane with everything else. I don't know how else to describe it. I'm going to draw a different molecule, and instead of a methyl group, I'm going to have it be a little bit bigger just so that you could see the hindrance going on. All right, I am going to show you guys the most stable conformation of cis 1-ethyl 3-isopropyl cyclohexane. Because it's cis, it doesn't specify whether it's a wedge or a dash. It just says that they're both either wedges or they're both either dashes. I'm going to show you it both ways, and either one would be correct. So we're going to start with a line kind of downwards. And then around halfway from this line, we're going to go underneath and do a parallel line, as parallel as you can get it, around the same length. Instead of connecting it by going up, we are going to connect it going out, and then you connect them. Out, and then you connect them. Same thing again. Parallel line, slightly underneath it. Out, then you connect it. Out, then you connect it. These are really great examples of how quick, easy, and repetitive drawing chairs can be. And then I'm also going to show you how to do a ring flip. It is the exact same process, but just backwards. You know how we started this, drawing a line slightly downwards? Now I'm going to draw a line, but make it upwards. Okay? Same exact process. About halfway, I'm going to go down and draw a line as parallel as I could get it. So I'm going to do that. Now, instead of connecting it going down like that and then like that, I'm going to go slightly out and then connect it. Connect it. I'm going to do the exact same thing over here. Sorry. Line up. Underneath it, I'm doing a parallel line. I'm going to go slightly out to connect it. I'm going to go slightly out to connect it. Now I have my chairs and the ring flips. What happened here? Well, let's say this was carbon 1, 2, 3. When you do a ring flip, it just moves everything over one. So here, this is going to now be carbon 1, 2, 3. Now, so we already had carbon 1, 2, 3. It's ring flip 1, 2, 3. So this is, if you were asked to draw on an exam, draw this structure in a chair conformation and its ring flip version, this is how you would set it up. So now let's go ahead and represent them. Because these are both on wedges, they go up. When these are on dashes, they go down. Right here at this position, a wedge going up will be equatorial. And it looks like that. And then at position 3, we also have that on a wedge, and it is also equatorial. At position 1, if we were going up, because it's on a wedge, it is axial. At carbon 3, going up is also axial. So I'm going to bring this down a little bit to compare and talk about which of the two are more stable. I want you to notice these guys, they're minding their own business. They're pretty far apart from each other. Whereas here, these guys are a lot closer together. Okay, I'm going to try to draw the same size circle here. Do you see how these guys are not really interacting much? Whereas these guys, there's a lot of interaction. We want as many groups and our biggest groups to be equatorial if possible. So if I had to pick between the two and ask which one is most stable, this is our most stable. Why? Because they are both equatorial. When they're equatorial, it is our most stable conformation. Now, if I had to do the same thing, but let's say they were placed both on wedges, this means my lines are going down. Their position 1 is axial, so I'm going to draw it going down, and then it's an ethyl group, so we have 2 carbons attached to it, so I attach carbon 1, carbon 2. And then at position 3, it is also going down, and this is also axial. Again, do you see how close together these are? There's a lot of interaction happening. And now let's draw the chair flip version. At carbon 1, this is equatorial. At carbon 3, going down is also equatorial. These guys are the exact same structure. However, do you see this versus this? Who do you think is more stable? This guy is absolutely more stable. Why? Because they're both equatorial. So if you have an exam question and you are asked to select the most stable conformation of this or this, I want you to start by crossing out all the answer choices that have the least amount of equatorial positions. So if you have a bunch of chairs drawn out, I would automatically cross out this selection. I would automatically cross out this selection. And then you would just pick whichever one is the most stable. In this case, these are both the exact same structure. You would not be given these answer choices on an exam. What I have seen a lot on exams, I see this a lot on exams like this. They will give you, let's call this one of our answer choices as well. Okay. And then they will give you, I'm going to just duplicate this. It'll be like this. Let's just say we cross out all the ones that are just axial, and now we're down to two options. For the sake of pretending, let's pretend that this is axial and this is equatorial, just so that it's a tiebreaker now. Okay, this is equatorial, this is axial. Okay, and again, this is not axial, but if you were on a multiple choice exam, you cut it down, and now you have two answer choices left, and they each only have one axial group and one equatorial group. Look at what the structure is. 1 ethyl, 3 isopropyl cyclohexane. This is not 1 ethyl, 3 isopropyl cyclohexane. This is 1 ethyl, 4 isopropyl cyclohexane. This is a really good tricky question because no matter if it looks the most stable, it's not the right compound. The question wasn't asking about this compound. The teacher was just trying to trick you. So I hope that you all learned a lot from this lesson about how to draw a chair, how to draw and remember the substituents, whether they're axial or equatorial, how to determine the most stable conformation of a structure, and how to go about a multiple choice question. Again, cross out whichever ones you think are going to be the least stable. So if they have the most axial positions, and then before you select your answer, make sure it is the compound that you are being asked about, okay? This will be a trick question on there. I hope you all enjoyed this video. I will see you in the next one.